All right, greetings everyone. This is our second video for section 2.1, continuing on the stuff we discussed in the first video. I will say this video is a little bit shorter. We have a little less content to get through, but it is important stuff nonetheless. Okay, so if you recall in the first video we were talking about the differences between secant lines and tangent lines. And I'm going to go to this animation here on Desmos. If you recall, in this picture, the blue line there is a secant line because it hits the graph at 2 points. And then a tangent line is the green line because it hits the graph at just that single orange point there. And we saw that there was a relationship between these two, in that if we took this lead point right here, this one that I just circled in yellow, and if we move it back towards the orange point, then that secant line slowly becomes a tangent line. So looking at how this happens, if I take now and slide that point back, okay, you'll notice that as it gets closer to the orange point, I'm going to pass a little bit right there. Once it gets right to the orange point, then what we have is that the secant line has now become a tangent line. Okay, so, and we spent some time in the last video finding slopes of secant lines, and then we used them to estimate the slopes of tangent lines. So something you may be wondering then is, why can't we just calculate the slope of the tangent line? You keep talking, Cody, about these secant line things here, but you haven't said how to find the slope of the tangent line. So let's think about this for a second. So I'm going to draw a little picture here. So here's a coordinate axis. Let's say this thing I'm going to draw in red. This is a graph. And I'm going to select a point here on the graph. Let's call it this one right here. I'm going to call that point x, comma, y. So just an input and an output. Okay, and I'll draw a tangent line here, because that's what we're interested in, is finding the slope of this tangent line. And I know the tangent line's off a little bit. We saw in the last video that when we were trying to find the slope of a secant line, we took the slope between the 2 points. Well, in a tangent line, we're taking those 2 points, and let me say this was our, let's say this was our first point here. Okay, and we're making them closer and closer together, right? So I'll call this point A and B. And so if I slide the two together, then obviously A gets closer and closer to X, and B gets closer and closer to Y, until when we get to the tangent line, those 2 points are actually the same. So it's like we'd have, as this point moves back here, right, AB, the point AB, will become the point XY. Okay. And so when we go to calculate our slope, then using our formula y2 minus y1 over x2 minus x1, well, what we're going to see is I could call this my y2 and this my y1. And this my x2 and this my x1. And if we plug those into the slope formula, what we end up with is y minus y over x minus x, which is going to give us 0 over 0, which is undefined in math. And we can't talk about lines with slopes undefined. Those are usually vertical lines, but if you look at the tangent line over here, it definitely does not look like a vertical line. So that's why we can't just calculate the slope of the tangent line, and we have to use these secant lines to try to estimate them. Okay, so what I want to do now is look at a connection to instantaneous velocity. So finding these slopes of tangent lines relates to trying to find instantaneous velocity of objects. So what we have here is that the height h in feet of a cannonball t seconds after the cannonball is fired is given by that function h of t equals negative 3t squared plus 12t. Oops, sorry about that. So this one here. We have to find the average velocity of the cannonball over each of these intervals here. Now, as you can imagine, this connects to what we've been doing. So probably finding this average velocity is going to relate to finding slopes, right? And so when we do that, we think of this slope here. Oh, my Lord. Going to use the formula, again, our y2 my stylus really does not like this spot on my, here we go, y2 minus y1 over the x2 minus the x1. And as you can imagine, these t values right here, you see those are our input values for our function. So this would be like our x's, and then we have to find the corresponding outputs or y's. So we would do, plug in the first one, so do h of 0 Okay, so we plug that into the function up there, you'll see you get 0. Do h of 1. Plug that into the function above, and we would get 9. So plug that information into the function up here, so we'll have 9 minus 0 over their corresponding input values. 1 minus 0 equals 9 over 1, which is 9. Let's also think about units here. So they tell us up above that the t values, those stand for seconds. And then the output is the h, the value h in feet. So that tells us that these numbers here, the 0 and the 9, they have units of feet. These numbers here, the 0 and the 1, they have units of seconds. And so if we use those up above, we see that this 9 here should have the units feet. This 1 here should have the units second. So this would be 9 feet per second. Okay, and that's going to be the average velocity over that interval. Okay, so your job now for classwork is to find the average velocity over these other 3 intervals. So this one, and this one here. And they're going to use that information to try to estimate the instantaneous velocity of the cannon at the moment it is fired, which, as you can imagine, the moment it's fired is at time t equals 0 seconds. Okay, so you do that classwork on WALMAP. There is a classwork assignment set up for you on there. You can just do your work on your own paper and then input the answers onto that section 2.1 classwork assignment. If you have any questions, let me know. Thanks for watching.